everyone. My name is Dave Southwell. I own a company called Deft Computing, work with a lot of founders and startups, and effectively function as a fractional CTO. And I'm here today with Anne to talk about deploying GenAI RAG application to the cloud in a cost-effective way without a lot of extra overhead. Some of the benefits of using RAG in combination with large language models: it allows you to do three major things. One, it reduces the hallucination risk of a large language model on its own by augmenting the large language model with various other different sources of data that are oftentimes much more fine-grained and detailed. And because of that fine-grain and detail, you reduce the risk of hallucination, and you also improve the quality and authority of the responses that you give back. Another benefit of leveraging RAG is it avoids the cost of fine-tuning or retraining a large language model because it leverages the existing foundation model. And you can also utilize many available components. There's lots of stuff out there for you to use to get started. On the right-hand side here, you can see the high-level components of a GenAI RAG application. So you've got a query where the user might sit in the kind of far upper right corner, an embedding model, which converts that query into vectors, which are then sent to the vector database with retrieved context and a large language model, which then spits back a response. So there's lots of options for hosting this kind of a workload. However, self-hosting your large language model and RAG application can have a lot of advantages. Cost is one of them. You can self-host and you can optimize your cost structure. Scaling, a lot of the services out there impose rate limits on their APIs. You can also reap some better performance in the form of lower latencies if you self-host because you're not dealing with noisy neighbors. You can also exercise a bit more control over your entire stack because you're running it and maintaining it and deploying it all yourself. And privacy, you can keep it all to yourself. You don't have to share, you don't have to transmit any of your usage habits or your retrieval habits with any of the third-party services. You can keep it all in-house. The focus of our talk today is to explore and present to you an example reference architecture for how you could go about self-hosting your LLM and RAG model. There's some downsides to self-hosting. Among those is the additional operational complexity. It requires efficient and effective infrastructure management. And that's one of the things we're going to focus on today. The example that we're going to show today covers deploying multiple Kubernetes clusters across multiple clouds. And it also is going to leverage a resource-aware policy-based cluster scheduler. After that, we'll show how you can take advantage of lots of different automation and basic model management operations as well. We have all of the demo materials that Anne's going to show you later on in the talk are available on GitHub, so you can feel free to download and play with that. At a high level, we've got a raw data source. Probably it's an unstructured data source. We've got an ingestion job to create or update a vector database where we're going to store and retrieve our RAG contexts. And then we've got an LLM and RAG serving component, which contains the prediction service and combines the model input and query with RAG contexts that are fetched from the vector database. That all gets pulled into one prompt and sent off to the LLM serving to obtain a query response, which will then send back to the user. All right, let's talk now about some of the resource needs for each one of these components. In terms of the ingester layer, the vector database, those are going to have nominal CPU needs and resources. And we're probably not going to need those to be available and up and running all the time either. The middle layer here, the LLM RAG serving and the vector database itself, along with the user interface, that's going to have much higher uptime requirements. So we're going to need high availability there. But it too can run on pretty generic CPU resources. Last but not least, our LLM serving component, which is going to require the GPUs. And it's also going to be used on an ongoing basis. It has, high availability needs, but maybe not quite as high as the LLM and RAG serving component. The nice thing about the resource-aware scheduler and policy-based scheduler is that you can define those policies and you can define the resources that each one of these things needs and be able to dial this in to whatever your specific requirements are. How do we meet these resource needs? Multi-cluster cloud Kubernetes is well suited. Kubernetes is a nice way to organize all of these resources as well, so it keeps things neat and tidy. You can leverage even things like GitOps to make it really easy to spin things up and spin them back down. Another reason Kubernetes is great for this is because it allows to aggregate the management of similar resources. So we've got some Kubernetes clusters that have a GPU and some only have CPUs, and we can find the best combination of cost and location to meet our policy requirements. All right, so how are we going to do all of this? We are going to leverage a policy-based cluster scheduler because it can automatically place workloads for the model rollout across all the different components that we talked about, whether it's the RAG serving component, the LLM serving component, or the vector database. There's a few different options: Karmada, KCP, and Nova. This talk is going to focus on Nova. Nova is a control plane cluster scheduler, and it sits in Kubernetes, and it uses policies and resource availability to select workload clusters for placement across various different cloud providers and clusters. You can migrate your workloads. You can do just-in-time clusters, and this is supported across all the major Kubernetes as a service providers out there. So EKS, GKE, and AKS. All right, so let's get into some specifics on the example deployment. So for the raw data source and the vector database itself, the ingester, in our example, we can use FAISS, which is a vector database built with Hugging Face embeddings. And then for our embeddings, as a raw data source, we've got some Hugging Face embedding. For the LLM and RAG serving component, we can leverage LangChain. On the bottom end there, for the LLM, we can use OpenLLM and leverage Hugging Face LLM model, the MosaicML one. Since we're going to be deploying everything in Kubernetes, we need to make sure that we've got everything that we can put into containers. And if we need to load things in from S3, we can go ahead and do that as well. LangChain used for Docker loaders and splitters and interfaces. We've got Hugging Face embeddings, and we've got FAISS as our vector database, which is pickled for S3 upload. You can see an example of the packaging, the Docker container packaging, if you click on that link there. Center section here, we've got for our LLM and RAG serving component, we've got LangChain and Fast API and FAISS libraries and the vector database to facilitate S3 download and unpickling. You can actually deploy multiple instances of these along with a load balancer sitting in front of it. So that's how we're going to get our high availability from this as well. Last but not least, down at the bottom, we've got our large language model using OpenLLM. Does have a requirement on an A10G GPU, and we're actually going to deploy multiple instances of this as well and sit a load balancer in front of that. Let's talk about some of our Kubernetes clusters needs to support this. In our reference architecture, we're going to use one cluster for the vector database and ingester piece, along with the raw data source. The availability and uptimes on this component are not as high as the other two. So we'll just use one cluster for this. And for our LLM and RAG serving component, we'll use 3 clusters, mainly to spread the load and spread our availability or risk of downtime across 3 different regions. We picked US, Europe, and Asia. And last but not least, we've got our LLM serving component, which is going to have 2 clusters. So pretty high availability, not quite the same as our LLM and RAG serving component. But then again, for our use case, we don't think that it needs the same uptime requirements. So take a look at how Nova would do the deployment across these different clusters. It's a 4-step process. The first step being establishing the model namespace and image pull secrets across all the different workload clusters. So you can see on the left, under US West, we've got our RAG serving cluster and our LLM serving cluster. They both get their model namespace and image pull secrets so they can pull the containers and run them and all that kind of good stuff. The next step would be for one of the LLM serving clusters to place the LLM serving model and the load balancer and get an external IP going for that. Eventually, we would do the same for the LLM serving cluster 1, add that to the load balancer that we deployed for LLM serving cluster 2. Next, we deploy the vector database over on the VectorDB ingester cluster 1. And last but not least, we deploy our LLM RAG serving front end, basically with external IPs across the 3 clusters in US West, US East, or EU, Europe West, and Asia Pacific Northeast. There we've got our front end, and then we've got the primary backend components, the vector database and the LLM serving models across the other 2 clusters. Pretty simple to define in Nova and pretty simple to kind of understand conceptually. How can we undeploy all of these things? How can we remove it? Just get rid of the namespace, because everything that you deployed for all these things, you deployed into one namespace. Yeah, just to kind of sum up the model components, we've got the open source versions of this. We've got FAISS, Pickle, and S3 for the vector database, but you could use an off-the-shelf solution for the vector database and pickling and unpickling with S3 in the form of something like AstraDB from DataStax, Pinecone, of course, and Weaviate. The model cloud infrastructures, you could locate workload clusters in a single cloud or in multiple clouds. You could also enable a cluster standby in either suspend or resume or delete, recreate mode, or disable standby. So that's that just-in-time cluster provisioning that we talked about at the beginning. In terms of model operations, you could trigger a model rollout via GitOps. You could also run multiple versions of the model, blue-green testing for new model evaluation, capture more data, iterate. Something like this reference example that we showed in using something like Nova makes it easy to deploy different versions of your model. So easy. If you think back to it just being all about the namespace, everything goes to one namespace. It keeps things nice and neat and tidy and well organized. And you can also make an old version, set it up for retirement, and you can have all the benefits of version metrics that are associated along with that. Anne is going to take over from here and go through the demo that she set up. All the code for this is on GitHub, and we hope you enjoy what we've come up with. Thank you very much.
All right, thanks very much, Dave. So now let's move into actually see where the rubber meets the road of actually seeing how you would do this approach for real kinds of operations you would do when you're managing an LLM plus RAG model in production. So we made some choices around those choice spaces that Dave mentioned. We actually substituted the AstraDB for the FAISS database, but in our repo we show both. It's very easy to substitute one for the other, but we just thought maybe people in production wanted to go with one of these more commercial sort of vector databases. But either one works fine. So I've got the packaging here for this database being built with the Docker. Earlier on the top, you saw that we had links to the packaging for using this other vector database strategy. Our strategy is to read the vector database in when the first version of the model is deployed, so it's not being continuously updated as a choice point. We actually deployed on a single cloud, which is EKS, but in various regions on that cloud. And we actually enabled cluster suspend resume, which means when a cluster is completely idle for a certain period of time, we scale down all of the non-control plane resources, so the resources that the user owns. This is an option. This is not on by default. You may or may not find this interesting. It's not key to the demo, but we thought you might enjoy seeing how that would play out with the demo. And finally, the operations are triggered manually for the purposes of doing a demo. But I agree with Dave that GitOps can be a good way to do these operations automatically on certain things that happen. So just a couple of disclaimers. So this is not about my mad skills at ML, which are, I don't play a data scientist on TV or anything like that. So this is about resource management. So I think we chose reasonable embedding for the vector DB. We chose a MosaicML model for our LLM, obviously great choice. But a different choice might be more appropriate for you, and you would tune that. And we didn't spend a lot of time tuning the resource sizing of the Docker containers. We just made them the size that would work for the workloads that we were running, but that would be also a thing that you would tune in production. So at the beginning of time, we have Nova managing 6 clusters. The first 3 clusters are CPU clusters on which we're going to deploy that LLM plus RAG serving component that talks with the user. On the 2 GPU clusters where we're going to deploy the LLM model that's running on a GPU to deliver the LLM results. And the ingestion cluster is where we're going to run the ingestion job to set up the vector database. So at the beginning of time, they're all ready, meaning that each of those clusters is heartbeating back to the Nova control plane. They're all idle, but they're not in standby because not enough time has gone by for them to enter standby. They've all entered standby. I just waited a while to see that so that we start the demo with them all in standby. This is just, I guess, kind of an interesting initial state. So basically, what we have here is a situation where it's a very simple, Dave said it was simple. Let's see if people think it's simple. But basically, it's a one script to do a model deploy. And so that script basically, and this is in our repo, but that script basically consists of a series of operations, regular Kubernetes operations against the Nova control plane to deploy the policies that you want and to actually then deploy the things that, the components of the LLM plus mag model that are going to be governed by those policies. It's a very short script to do this, and we'll basically show you the output of running that script. So when we, excuse me, when we execute this script, we give it some parameters. We tell it the namespace we want to deploy into. So that's the first parameter. We give it the secrets that it's going to send out to all the different clusters that are participating. We tell it true, which means I would like you to deploy the vector database this time. I'd like you to read in the raw data and deploy that into the vector database. We tell it, where the ingestion cluster is. We give it the ingestion cluster's name because the policy for the ingestion cluster is going to be based on name. Then we give it some information about what we're going to ingest. In this case, we're going to ingest a sitemap, and the sitemap data is there, and that's basically the public documentation for Elotl, so that's what we're going to use for our Q&A, RAG Q&A, and then some information to basically run the AstraDB. The first step is to deploy the model namespace and the image pool secrets. And so this is using the policy of spread and duplicate. And so just to give you a sense of what that policy looks like, it's very simple. So you see it's saying a spread and duplicate, apply this policy to things that match this resources, group them by this name, and apply it to any namespace. So it's a pretty simple way to write the policy. And so we can see then when we deploy the namespace, it's using the parameter that I sent in of where I want the namespace deployed, and it matches that label, so the policy will apply to this. And so Nova will schedule this on all the workload clusters. So it'll spread and duplicate it across those clusters. And same thing for the secret. So next we're going to deploy the LLM serving thing, the thing that needs GPUs. And in this case, we're going to use a GPU availability policy, but basically a resource availability policy. Again, the policy is simple to write. I'm going to match things that have this label. I want them to be matched within this namespace so that the GPU usage within this namespace is kept together. And I want it done with everything that can be basically can accommodate the resources needed for this. So this is a resource availability policy. And so we see it deploying. And here's the deployment. Basically, I'm going to show you quickly. So here's the deployment. It matches the namespace, it matches labels. So it's going to deploy and satisfy these resources. Now I just asked for one GPU basically, and just an arbitrary amount of CPU memory that would work. And then here's the service that's also going to be governed by that policy. So these things are going to be deployed on a workload cluster that can satisfy the need for one GPU. And I should say that both of my GPU clusters, each one only has one GPU machine, because I wanted to show resource availability, so I needed to be kind of sparing of the resources so that a simple example would show that. So that's what's going on there. So this is a resource availability policy. It will deploy and it will return the external IP for that LLM that is deployed. We'll now deploy the vector DB ingester job. So the policy here is to deploy a specific cluster, and so here we're passing in the cluster on which it should be deployed within that namespace. So that's the policy. That policy matches this job. So it will basically run this job on that cluster that matches the thing, and we'll wait for the job to complete. So that's using the specified cluster policy. And finally, we're going to put those three front ends on the three clusters that are in the different regions that will allow users to talk within the region. And so we have a spread policy, but we don't want to spread to every machine, or every cluster the way we did with the secrets and the namespace. We want to spread to a select group of clusters. So we've labeled the clusters that we want to spread to in Nova. And so our policy now is to spread and duplicate, but to only spread and duplicate across this cluster selector. And so this is the label that we put on the clusters. And so now when you see this deployment happening, it's happening for, this policy will make this deployment happen across the three clusters that match that capability. So when we come here, so we're finished, and we ended up with the three external IPs, an external IP for each of the three duplicate services that were put out on the three clusters in the regions. And so now we can make a query to that model. I'll just choose one of the three regions. I mean, we could put a load balancer in front of this, so it could choose which region is close to me or whatever, but I'll just choose one of them. I'll choose to query against Asia Pacific, and I'll ask it what backing store does the Nova control plane use, and it gives me the answer I expect, which is that it use etcd for its backing store. So it got the right answer, so this is cool. So after model rollout, we see that the 6 clusters are now in a different state. The 3 CPU clusters are all not idle anymore. They're running those jobs waiting for customer queries. And one of the GPU clusters is also busy because it's serving the LLM model. So that's the state we're in now. So deploying the second version of the model is very similar to deploying the first version. Same, we have a different namespace, and we say false to the building the vector DB because we've already built it, and we'd like version 2 of the model and version 1 of the model be comparable, so we can make sure that version 2 performs well before we retire version 1. So we don't want to change the vector database right away. At least that's our thinking, is we want to be able to compare their performance and evaluate their correctness. So same script with a few different parameters. We get the IPs, we make the same query, and we get the same answer. So through the simple evaluation, at least it seems to be working well compared to the other model. So at this point, both of the GPU clusters are now busy. So this shows that I had to choose the second GPU cluster because the first one only had one GPU, and that GPU was not available anymore. So finally, we've decided, let's say, that version 1 is no longer needed because we're happy with version 2 of the model. So we want to retire version 1. So basically, all we do is delete the namespace. So now that first GPU cluster that we were using for that first version of the model is freed up again, it's idle again. So this is the state we're in. So it's super easy to get rid of everything. So that's basically the basic example, and you can imagine that you might have multiple models deployed at the same time, multiple versions, but these are the basic operations you would do. The second example is just a variant on the first example, but the key thing here is, what if you need more resources than you statically have? So in the first example, we had these clusters that were all set up, and we only had 2 GPUs essentially. We had 2 clusters, each one had 1 GPU. But what if you occasionally wanted to run with more than 2 GPUs? Because occasionally you needed more resources. So this is intended to illustrate that. So basically this time I want to have 3 versions of the model in flight. And I want the third version to use on-demand resources. And the way this can work is that the Nova scheduler understands that there could be an autoscaler running in the target cluster. So it detects if there's an autoscaler running in the target cluster. The 2 autoscalers that currently is able to detect, one is the Kubernetes cluster autoscaler, and the other is the Luna cluster autoscaler from Elotl. And so if it detects there's a cluster autoscaler and it can't find available resources in any of the clusters that were already available, it schedules to a cluster that has an autoscaler with the idea that that cluster will take care of it because it has an autoscaler there. So basically it fills and spills. It fills the existing resources, it spills to letting the autoscaler get more resources if necessary. So this is exactly what we did. I put the Elotl Luna cluster autoscaler on one of the 2 GPU clusters. So when we and deployed the version 1 and version 2 of the model, just like we already saw. But when I got ready to deploy version 3, it stayed pending because there weren't enough resources. So basically, for version 3, I then annotated the YAML to do the deployment to say I'd like the autoscaler to handle it, And actually, I would like the autoscaler to handle it with a high level of GPU machine. So basically, autoscalers typically, or at least the Elotl one, tries to give you the cheapest thing that it thinks will satisfy you. I don't want the cheapest GPU, I want at least an A10 G, so I'm telling it that model here. And you can tell it, by family or whatever, but I'm actually specifying the exact machine that I want in this case. So at that point, it will spin up the cluster. Nova will schedule on that target cluster, and that target cluster's autoscaler will spin up another GPU machine. So now we have 3 copies of the model, right? So yay. Now you might wonder what should happen if one of the 2 versions that I had on the static resources gets retired. The answer is, what do you want to have happen? I mean, you could have basically the version 3 continue to run on the scaled out cluster because you figure eventually somebody will use the static resources and you don't want to disrupt the thing that's running. That would be one strategy. Another strategy would be to basically modify, you can script this, modify to pull off that autoscaler annotation and let Nova reschedule, so Nova has the ability to reschedule and retarget workloads. That would be a little disruptive, but then you could pull the thing back from the autoscaled node into one of your static nodes. So really up to you what your use case is and what you would prefer. So basically we've shown you what we think is an easy and efficient approach to self-hosting production LLM plus RAG models. It uses multiple cloud Kubernetes clusters to group resources that are related. It uses a policy-based resource-aware cluster schedule to manage those multiple cloud Kubernetes clusters. And we presented how to use that system to do common operations that you would need for model production, like model rollout and model retire. So we really appreciate you taking, today is Pi Eve. I guess I don't know if anybody's celebrating Pi Day tomorrow, but we really appreciate you coming out late after work to celebrate Pi Eve with us here and listen to this talk. And like we said, all the things we did are in repo, Git repo, which is linked in here. And also you can try these Nova and Luna components yourself.
Just a quick word for everyone. I'm going to try to make this a little interactive, so if you have any questions, just raise your hand and we'll take them as they come. So yeah, quick intro to me, as Kobie said. My name is AJ. I'm the engineering manager for the GenAI training platform team at Databricks. Formerly was very early in Mosaic and then came over to the acquisition. And yeah, I will be talking about scaling to the future, what it really takes to train your own LLM from scratch. So before we get into how to train LLMs, just a quick LLM primer for everyone. What is an LLM? Simplest way to think about it is fancy autocomplete. What it's basically doing is saying, complete this sentence as you have seen other sentences completed before. Sounds really simple, but if done really well, gives access to a ton of different applications like question answering, chat, code completion, assistance, retrieval augmented generation, commonly known as RAG, and a whole bunch of other things. So, how does training an LLM actually work? Fundamentally, what we're doing is feeding in data in the form of sequences of tokens. And you can think of a token as very roughly a word, into the model, and then training it to predict the next token, otherwise known as word. So if you look at this picture here, as a quick example, we have a sequence, Humpty Dumpty sat on a blank. We feed that through the model, and over several training iterations, we'll train it to predict the word one. This is basically how an LLM works, and under the hood, what it's really doing is this sequence is a vector of numbers, and the model is actually a bunch of matrices of floating point numbers. And what it's really doing under the hood is just a whole bunch of matrix multiplies, and that's actually why LLMs are trained on GPUs, because GPUs are very good at multiplying very big matrices very fast. So, when you're training LLMs, the first letter is L. LLMs are very large. The data is very large, the model is very large, and oftentimes you cannot just use one GPU or even one machine. You have to do distributed training across many GPUs and many machines. So I have a small example here. It shows 2 GPUs, but in practice you actually have like dozens or even hundreds of them. And when you're doing this training, you have your data set. Your data is split into batches, and then each batch is split evenly across all of your GPUs, kind of as shown here. So you have your data split across the GPUs, and then you have your model. And your model, like I said, is just a bunch of matrices of weights. That is also split across all the GPUs. And the reason is that typically the model cannot fit in the memory of just one GPU. There's a whole bunch of ways to shard the model. I'm not going to get into the details here. Just know that that's like its own research area to an extent. The important thing to know about training LLMs is that training involves communicating a lot of state between all of the GPUs at every iteration of training. So it's really important to have really high throughput networking and interconnect between the GPUs. Otherwise, you're going to spend all your time communicating and no time actually doing the computation on the GPU to train the model. Last thing you want to know is, like, obviously, because training takes a long time, you want to take periodic checkpoints throughout the training process. So now just talk a bit about the scale. So this actually depends on the type of training you're doing. There's typically two main types of people refer to. There's pre-training, which is training very large models from scratch on very large data sets. And then there's fine-tuning, which is taking an existing, like, already trained model and just tuning it to a specific data set to do well on some specific task. So if we're talking rough orders of magnitude in terms of, you know, these different categories, data size, we're talking about like hundreds of billions to like even tens of trillions of tokens, like roughly words. Model size, single-digit billions to hundreds of billions of parameters. Cluster size, you know, tens to even thousands of GPUs. Training time, hours to like months per a single model. And cost can be, I wrote tens of thousands, it's actually more like tens of dollars for like very small runs to like tens of millions of dollars for like the really big training runs. For the rest of this talk, I'm going to actually focus the most on the bigger stuff because that's where all of the systems challenges really come in. So typically, what does it look like to train a GenAI model? So this is what we call the GenAI training stack. These are all the things that you need to go well in order to actually train a model. So at the lowest level, we have device drivers and toolkits, like the things that interface with the GPUs. Then we have deployment and orchestration, like how do you actually manage the GPUs? Deep learning libraries, used for actually implementing the code that trains the model, distributed training frameworks, higher level abstractions, data loading and processing, how do you actually get the data in to train the model, and then experiment tracking and tools. So, fun story, prior to acquisition, Mosaic actually delivered everything from data processing down. Post-acquisition, because of Databricks, we actually now have experiment tracking too because of Elotl. So it's really like the whole end-to-end picture. So some challenges with training LLMs. Number one, software stack complexity. That stack I just showed you is very complex. And in order to really train LLMs well, you have to get every piece of that stack right, from the bottom device drivers all the way up to like the data loading and everything in between. Second, GPUs are very scarce. So cloud providers don't have very many of them. It's hard to get them. You need a lot for training. Third, even if you get GPUs, training is like very expensive. As I mentioned earlier, like the most expensive runs that even we've seen are like tens of millions of dollars just in GPU cost. And fourth, and this is actually, if there's anything I want anyone to get out of this talk today, it's actually this fourth point. Training LLMs is very much a difficult operations problem, more so than anything else. You're running a big distributed system where failures happen all the time, and really dealing with those failures is more about operations than anything else. So now we know the challenges. We're going to transition a bit into talking about how we built the Mosaic training platform in order to actually address all of these challenges. And by the way, quick reminder, if you have questions, please just raise your hand. So the Mosaic platform is a multi-cloud training platform for LLMs, but really you can train any model on it, built on top of Kubernetes. And what we really did was build this platform with the goal of completely abstracting away all of the complexities I just talked about, all the device drivers, the GPU orchestration and management, the data loading, just abstract all of it away so that ML engineers and ML researchers can focus on turning their data into models that are relevant for their applications and don't have to deal with all of that like nitty-gritty in the middle. So time to kind of break down that statement I made earlier. First, like why multi-cloud? So there's a few things that multi-cloud buys us. First is it lets you go wherever the GPUs are. It mitigates the scarcity problem. You can go to wherever the cloud has your GPUs. Second is actually, it mitigates cost a little bit too, because if you're able to go to any cloud provider, you actually have much more negotiation leverage in getting the GPU deals. So you can negotiate lower prices. Third is actually more about data egress and compliance. Like certain people and certain customers can only have their data in certain places. So you want to be able to train where the data already is. So by operating a multi-cloud training system, you can actually do that. Second, why build on top of Kubernetes? So there's actually good and bad for this. So I'll start with the good. First, Kubernetes, as everyone knows, is a cloud-native compute abstraction. It's also very extensible. It's actually pretty easy to build your own custom controllers and plugins. So if you need to do any specific stuff for GenAI, you can build those. And I'll actually talk about some of the ones that we built. And third is there's a bunch of useful built-in primitives for applications like services, config map secrets. Anyone who's familiar with Kubernetes would know what these are. That are also good for building this. But even though there's these things, Kubernetes is also missing a bunch of stuff. The biggest thing it's missing is actually built-in gang scheduling. For anyone who's not familiar with that, what it basically means is you have a bunch of machines that you want to schedule on all at once, like all or nothing. This is not something that Kubernetes has natively. Second is if you're operating a cluster with many users, you also want some advanced queuing capabilities on top of gang scheduling, things like priority, preemption. This does not exist natively in Kubernetes either. And third, which is actually really big for LLM training, is GPU and networking fault tolerance is not built in. It's just not something Kubernetes really does, and it's super, super important for training LLMs.
Quick question about the previous slide. So when you said that you are able to go where the GPUs are, at what granularity are you choosing between multiple cloud providers? Within a training run, across runs, or?
It's for a single run. So you can imagine, like, I'm training a model, I want, the interface we provide is literally, and I'll show this later, give me 16 GPUs for this model, and then we go and find 16 GPUs across whatever cloud provider.
So subsets of these 16 are being satisfied within a run across
No,
runs?
it's all in one place. Oh, sorry,
Okay.
yeah. So the question was, like, at what granularity are we finding GPUs for a run? Is it, per run or per user or whatever else? And I was just saying it's per run. It's per run, and they all have to be in one place. And I'll actually show all of this later.
Thank you.
Question?
Yeah. You actually alluded to network bandwidth being a limitation, right, even within the same cloud. But if you're running a training across clouds, how do you mitigate and address network issues?
A single training run is trained in one cloud, in one region, and actually even more than one region. It's within a single block of machines, which I'm actually about to show.
Thank you.
By cross-cloud, I mean you can have different training runs that go to different cloud providers.
Okay.
Are you multiplexing your training jobs with other types of workloads, or is ICE exclusive, is it a training platform?
That story has changed over time. So we did a little bit of it pre-acquisition, and nowadays it's just training, but we're actually, the long-term vision is to still be able to share compute between applications. Yeah.
Or are different pieces of the AI pipeline, like inferencing, data pre-processing, is that all happening in the same cluster?
Well, data processing doesn't usually require GPUs, but inference and training we do want to eventually share compute, yes.
Okay, thank you.
Okay, I'll move on because some of the questions are actually going to be answered in a bit. So now just to get into some of the details about how we actually built this thing. So how to build for multi-cloud. So the first, there we go, okay. So first, very high level architecture for what the Mosaic platform looks like. We start with some clients. We have a CLI tool, an SDK, a web console, and then in the middle is kind of all the smart stuff, the training control, the orchestration, the fault tolerance, all of that is kind of there. And then on the right, we're just showing that, yeah, this thing can orchestrate multiple clouds all at the same time. So in order to build this system, the first thing we have to solve is actually scheduling. Jobs will come in from users. How do we find compute for those jobs? So to set the stage a little for what this looks like, jobs will almost always require multiple machines. We refer to this as a multi-node job. And when you're scheduling a job, it has to be all or nothing scheduling. So if a job comes in and requires like 16 machines, we have to give it 16 or keep it in the queue. There's no such thing as partial scheduling here. So that's constraint one. Second constraint is actually the networking. So in order to get that really high throughput interconnect that I talked about, that's important for training, you need to actually land the jobs in the same kind of network block. So in cloud provider terms, cloud provider has this thing called a placement group. And you can think of a placement group as literally a set of machines that are just physically wired together, and they give you a guarantee about the all-to-all network throughput between all of those machines. So if you look at this picture here, I kind of like showed what this looks like. So we have different clouds, let's say like AWS and Azure, just as an example. Each blue box in that diagram is actually a placement group. So it's a set of machines that are all networked together. Now our client is submitting a whole bunch of different jobs to our central scheduling system. Some jobs require 2 machines, some require 3, some require like who knows how many, right? The general point is now we need to basically bin pack these jobs in the machines in the different placement groups so that a job lands entirely in one and it's all or nothing scheduling. So for anyone who might be familiar with scheduling, this is pretty much an NP-hard bin packing problem that we have to solve. Obviously it's an NP-hard problem. We have some approximate solutions that we've built for this scheduling. But I think that addresses like the questions earlier about the networking and all of that. Cool, so moving on, I talked a lot about networking. High throughput networking is super important. 1632 gigabits is actually ideal. And cloud providers all have very different networking stacks. So AWS has Elastic Fiber Adapter, EFA. Azure, Crusoe, and CoreWeave all have InfiniBand. OCI has Rocky. GCP has this GPU Direct like TCP-X thing that they created. So in order to abstract all of these things away from users, because we don't want users to have to deal with like the networking devices and drivers for different clouds, we basically just have a bunch of custom images with different drivers installed that are automatically used by the users, so that they don't have to worry about these networking details. Third, so the other point is that if you're operating a multi-cloud product, it is really, really, really important to not keep long-lived state inside the cluster, because synchronizing state between clusters and cloud providers is a huge operational nightmare. Like imagine you have a data set in one cluster, and then you change the data set, and now you need to copy that change to every other cloud that you're using. So for this reason, we actually rely very heavily on blob storage. And for cluster storage, in Kubernetes terms, we only use ephemeral storage. So we're not running any PVCs or any sort of permanent storage in the cluster. So two things that matter, the data and the model checkpoints. So for data, we keep it in blob store. During the training run, the data is streamed in from blob store into the cluster, kept on ephemeral storage, and then deleted when the job is done. Model checkpoints, they're written to the ephemeral storage, they're asynchronously uploaded to blob store, and then deleted. So we don't keep anything in the cluster.
What's a PVC?
Persistent volume claim. It's just a Kubernetes term that means like it's some sort of permanent, it refers to a permanent storage inside the cluster. Yeah. Any other questions? Sorry, everyone. Oh, okay. So this little animation I have here actually illustrates the Mosaic like streaming data loader. So what it actually does is it manages a sharded data set, like a very, very big data set. And it enables us to actually only download the pieces of the data set that are needed by the specific machine for training. So you don't have to download the entire thing, so the data set might be very big, like terabytes in size. So I talked a bunch about how we built for multi-cloud. The next thing to go over is actually how do we do fault tolerance. So as illustrated by this Harry Potter meme here, fault tolerance is a very, very difficult thing. A model dies. Is it a dead GPU, some nickel timeout that happened, a bad cable, like who knows, right? Like so many different failures can happen. And this is really the problem that plagues like all of LLM training. Kubernetes does not do this, as I mentioned earlier, so we actually built the entire stack from scratch. And to give you guys an understanding of what the scale looks like, you can expect one failure roughly every 1,000 GPU days. So on a 4,096 GPU cluster, we're looking at roughly 4 hardware failures every day. And things like monitoring, triaging, resuming, debugging are all a huge, huge time sink. These are actually screenshots from our internal channels. And you can see on the left, it's like, oh, well, we had another node failure. And then after we built this whole monitoring stack, worst case scenario, you're like asleep and your model's training, something dies, and it just like detects it and resumes your run for you. So just to get into a little more details of the monitoring, so there's really 2 levels of monitoring that we care about. The lower level is the GPU monitoring on the specific machine, and then the higher level is actually the network monitoring between every pair of machines, because we want to make sure we're getting that high throughput. So the networking complicates things a lot. Before, if you don't care about the networking between the machines, if you have n machines, there's roughly O of n things that can go wrong. It's just monitoring each machine. Now, if you care about what every single pair of machines is doing, if you care about all of the networking between all of them, now you have roughly O of n squared things that can go wrong. It's like quadratic complexity as the number of machines increases. So it blows up pretty fast. In order to address this challenge, we actually built like a 2-tier monitoring stack. The lower level monitors all the GPUs and all the individual machines. And then on top of that, we're constantly sweeping all of the machines, all of the pairs, to find bad links and bad cables between them, to make sure that we get like very high throughput when we're training. So now, I talked a bunch about how do we detect failures. Like a failure might cause your run to crash. How do you actually resume? So 2 big points here. The first is because GPUs are very scarce, if a machine goes bad, you're not really guaranteed to get another one from the cloud provider. In fact, you're almost guaranteed to not get one for a while. So you oftentimes find yourself in the situation that's pictured here, where you have a bunch of machines, some of them die, sometimes a whole group of them die at once, and you still need to resume your run. So your run needs to be elastic. Your software stack needs to enable you to resume your run on a different number of machines than it was originally running on. So you launch your run on this many machines, it dies, you relaunch it on fewer machines. It also has to be deterministic, like you want this whole process to always be, deterministic, otherwise debugging is very hard. The second point is the resumption must be really fast, otherwise you lose a lot of money. Thousands of GPUs can mean hundreds of dollars per minute of resumption time. And resumption in this case means like, re-downloading your checkpoint, re-pulling the images, fast-forwarding your data loader, all of that stuff needs to be really, really fast. So now, question?
So how do you handle putting the system? So how do you handle putting the host back in your placement groups? Do you tear down all the hosts and put them back in? Or?
What do you mean by host in this case?
So for example, your nodes or your GPU, if you have the outages,
Oh, okay, I see, yeah. So the cloud, so what happens in, so going back to
like in AWS, or how do you get them back in your placement group?
yeah, so going back to this slide, so basically you, cloud providers will give us the ability to scale nodes up in a placement group. So what happens is we will re-request them, and oftentimes, like, in practice, what this involves is working with the cloud provider and saying, hey, like, these nodes are bad, we need to get more nodes in this specific area. It's part of the negotiated deal. Okay, sorry, going back. So putting it all together, what does this actually look like when it comes together in a product? So first, job submission. This is actually the interface that we expose to customers. Typically, you write like a very basic script, which we actually provide in a lot of cases to instantiate a trainer object. You give it your model, your training, your data loaders, all of that stuff. And then you launch a job with a config that looks something like this. You give it a name, you give it an image. The image is built by us. It has all the drivers installed, everything that I talked about earlier. You have a command which just executes your training script. You specify how many GPUs you want. So I want 64 GPUs of A100 80 gigabytes. Notice there's no cluster there. We will find the cluster and we will find the cloud provider where these are available. And then scheduling, yeah, we have some priority preemption stuff which helps like large teams manage their GPU allocation. So, like I said earlier, one of our big goals was to provide a single interface for all clouds. So you can see here, it's like, MosaicML, AWS, OCI, Kobie. We actually run on many other clouds. This chip's a little bit old, but you have all these clouds, and then you can submit a run. You can choose which one you want to submit to, or you can just like let us pick for you. But we abstracted all the way with that same interface that I showed earlier. Next thing, seamless scaling of GPUs. So you can specify the GPU number as basically anything, and we will handle scaling up your run for you. We'll handle all the multi-node configuration. The software stack is very elastic, so it can run on different numbers of GPUs, like I mentioned earlier. So you see here, it's like, okay, I'm running on 8 GPUs. It does some stuff. These are just telling the logs for a run. And now let's scale up to, I'm training a bigger model, 30 billion parameters, 256 GPUs, and it'll look something like, 8, 256. And then you can see, like, all of the ranks on each machine. Lastly, this is actually, this is sort of what it looks like when you're training a model. So you don't really need to pay too much attention to the actual line, but the point is that different colors are different presumptions.
You mentioned we'll select a cloud provider for you, but isn't it depend on where your data resides? Let's say my data is in US H1, so like it will always be in US H1, right?
Yeah, so 2 points to that. One, the data is in block storage. So some customers will tell us, I only want to use specific clouds, in which case it's really finding a region within the cloud provider, because there are different regions that have different numbers of GPUs. For customers who don't care as much about egress and they're okay with their data leaving, we actually have the ability to for them to give us ways to authenticate from different cloud providers, and then we'll just stream their data from like AWS Blob Store like into Azure, for example. Like that is something customers do. Any other questions?
Do the customers give you a budget, a financial budget for how much they're willing to spend to do this, or do you give them an estimate of?
There's a few different models. So we have an on-demand model where so the question was, do customers give us a budget? There's basically two models. There's an on-demand model, we just pay per use, like per training run. Then there's also reserved, which is customers that they really want guaranteed capacity, and in that case they pay us upfront, or it's a pre-negotiated deal.
Okay. And is there ever a problem with starvation? Like I want 16 GPUs somewhere and you just can't get them. Like that goes on, I ask for a large number and it just doesn't ever happen.
Yeah, so the question was, is there a problem with starvation? Basically, like there's just not enough GPUs to service the jobs, and I mean, yeah, all the time. And I think that's why we have a lot of queuing logic, that's why we have priorities. That's why we have like preemptible and non-preemptible jobs, is to actually more effectively manage that queue.
Okay. And the final question, I'm sorry to keep you so you said this is Kubernetes, but the customer doesn't know it's Kubernetes. You have Kubernetes clusters on their behalf that you set up?
Yeah, so the customer only sees this interface. They have no idea, like they don't, it's all abstracted away. Kubernetes is a complete implementation detail of the platform.
Okay.
Did you integrate with Kubeflow or other systems that allow you to do ML lifecycle end-to-end?
We did not.
This is the training part, right? But then you have other.
We did not. We considered it early on. So the question was, did we integrate with Kubeflow or any of these other like equivalent systems? The answer is we considered it very early on, but we actually did not integrate with any of them.
Until we got acquired by Databricks.
I was just going to ask about the Databricks.
Until we got acquired by Databricks, and then we integrated with MLflow.
That's what I figured.
Yeah, for experiment track. Yes. Any other questions?
Did you happen to use any of the open source priority preemption based schedulers for Kubernetes like Volcano Q, Unicorn?
We did not, and actually the big reason was because all of those schedulers you just mentioned are local to the cluster. we wanted to do this globally across clouds and across clusters, so we were not able to really make use of those. So all that logic is actually, it exists inside all the logic for priority preemption exists in this green box. It's like a central, what we call our control plane, and it orchestrates all of these different, what we call data planes, and that's where all the GPUs are.
And are your Kubernetes clusters multi-tenant in the sense that customers share clusters, or are you creating clusters per customer?
It depends, we have both options. It depends on the security model the customer wants.
And it's specifiable on the command line?
That is specifiable, basically like when the customer onboards, they tell us which ones they're okay with, and then from there we can route the job to whichever ones.
Okay. And do you ever run stretch clusters across regions? Did you have to?
No, we don't stretch Kubernetes clusters across regions because of the placement group problem. The placement groups only exist within a region and actually even within an availability zone. So we run single clusters per placement group actually because it will never make sense to run a job across placement groups. You just don't get the multi-node interconnect that you need.
Thank you.
Cool, so I only had a little bit more actually, just fast forwarding my slides a bit. Yeah, so basically each of these colors is a different resumption of the job. So you can see like, you start training your model, the loss goes down, boom, hardware failure, we detect it, we automatically resume the run, fails again, keeps going, and all of this happens automatically. The customer does not have to deal with it at all. And that's actually the point of, oh, I go to sleep for 8 hours and I'm worried that my run crashed. Well, great, we'll just like fix it for you. The system fixes it automatically. The right is just like a little, I guess more of a marketing illustration that shows that we can even like pause and resume jobs across clouds. So you start training on OCI, oh, we ran out of stuff there, okay, we'll move you to AWS. Okay, great, now we'll move to like GCP, right? So it goes across cloud as well. It's just some key takeaways. So first, multi-cloud helps you mitigate both GPU scarcity and cost. 2, stateless training, so not keeping any state in the cluster, it helps you easily switch between cloud providers. 3, Kubernetes is a great foundation, but you need things like advanced scheduling, fault tolerance capabilities on top of it in order to actually train LLMs. 4, fast deterministic elastic resumption is really crucial for large-scale training. And then the really big point that I want to make, 5, LLM training at scale is largely a systems plus operations problems for all the reasons that I just specified. It's really about getting the operations right and having the end-to-end system work. So yeah, any more questions?
You want, we got the mic right here?
Yes, it's a quick question.
Yeah, she's got it.
So how much work do customers have to do to make it work across different cloud environments, right? Or is this all taken care of by your tool?
It's largely all taken care of. Like it's really just that interface that I showed that we expose to customers, and different clusters might correspond to different clouds, but it's literally as simple as route it to this cluster or just let us pick for you. The only initial step is the authentication, like what I was mentioning earlier. If your data is in one place and we need to authenticate somewhere else, we have this concept of secrets built into our product where a customer can basically give us authentication credentials for different cloud providers, and that will allow us to stream their data set across clouds for them.
Okay, so they don't have to worry about how they want to architect their training and things like that now?
Nope.
Okay.
Most customers could not care less where we're running the job. They just want it to run on some GPUs. Yeah.
Okay.
Really interesting. Do you think that this, what you were saying about customers don't care about where they're running, do you think that's because of the current scarcity on GPUs, or do you think that all are like interchangeable?
That's definitely part of it. I mean, the only other case where someone would care is if they're worried about data egress costs, because egressing from a blob storage can be expensive, or if there's some compliance reason that says that they cannot use like a particular cloud provider. Those are like the real big reasons.
Slightly on a different note, like instead of LLM, like if you're talking about fine tuning on like on top of some already a large language model, do we have something similar? It's workflow for that as well, like that is managed by Mosaic or Databricks?
Yep, in fact, we actually, we have a fine tuning offering that's built on top of exactly what I just showed you. The interface is similar. It's a bit more abstracted, but yeah. Essentially, if you solve all of these hard problems for large scale LLMs, you by default solve every problem you need to solve for something like fine tuning as well, which is why I focus on the hard part. If you do that, you basically solve everything.
But let's just say I want to run like a OpenAI's model, GPT-4 model, but on top of the Mosaic. Like in that case, like it's like a double layer problem. Like we have like data, Mosaic need to go to the OpenAI's API to fine tune, right?
Yeah, if you want to fine tune OpenAI's model, we can't really support
I was
that.
saying through the like I have a data in data lakehouse, and like I want to go through the Mosaic, but use GPT-4 for example. I guess.
So you're saying, okay, so the question is like basically if you have data in Databricks and you want to like call OpenAI or something.
Yeah,
with
so
that
Mosaic.
data. Yeah, so then Mosaic doesn't really help you because you're making an API call to OpenAI. So there's no like training happening there. If you're doing fine tuning, then OpenAI is orchestrating it, not us.
And then just in the specific about how the Databricks platform broadly works, if you already have your data inside of Databricks and you're talking about what can you do with that, Databricks already has capabilities for proxying your requests over to OpenAI's API so that you can do that natively within the Databricks interface. It's just a matter of choosing which endpoint you want to work with from there. So yeah, like you said, it's not exactly a fine-tuning situation. It's more about like, are you leveraging OpenAI's API? But you can do that through Databricks' product as part of working in that platform.
It looks like a great product. Like, what are some open challenges that you still face? And
yeah, so there's a lot. Okay, so basically, first is the monitoring stuff is really hard. It's a long tail. It's a constant battle, and really what we found is that no matter how good your monitoring is and your fault tolerance is, there'll always be things you cannot catch when you scale. And then part of that problem becomes how do you have good systems and operations in place to deal with the times when you cannot catch things automatically. So that's one really big one. A lot of the other stuff is really just around, scale, and also like now that we're part of Databricks, we're actually trying to make things really work really well with the Databricks platform. So if you have your data in Databricks, then you can easily just like button push train models, train LLMs from scratch. So there's a lot of that work as well.
How much like cloud specific nuance and issues do you bump into like over the course of developing this thing?
So cloud-specific issues, also a lot. Yeah, I think some of the biggest ones were actually around the networking, which is why I highlighted that. Dealing with different implementations of RDMA and networking fabrics is very tricky. There's also like a layer above RDMA, there's actually this protocol, this library called Nickel, which was developed by NVIDIA, which is actually used for distributed communication across machines. Nickel works differently on different cloud providers, and we found that different ways of configuring Nickel is like work well or not well on different cloud providers. That was actually something we had to test a lot and figure out in order to configure it automatically for customers. Yeah, it's often the lowest level stuff that has problems.
So if I understood well, the control plane is yours, and the data plane is for the customer, right? So how are you monitoring the customer stuff?
That's a good question. So the question was basically who owns like the control plane and data plane, and yeah, so the control plane is ours. The data plane, so prior to the acquisition, the way we actually built this was we could run on GPUs that we own, in which case the data plane is also ours, or we run on GPUs that the customer owns, in which case the customer owns the hardware, but we deploy our software on that hardware. So we still have services that are running basically with the GPUs, and those services can egress information back to the control plane. So we don't do any ingress because you can't really call into a customer's VPC, but you can put services in and call out. They tend to be more okay with that. So that's how we did it. And that's actually how all of our scheduling worked. That's how all of our monitoring worked. We would just egress all the data back to the control plane.
So which means you have a plan for, you have an agent for every data plane or for every Kubernetes cluster?
So data plane and Kubernetes cluster are roughly one-to-one. You can have multiple, obviously a single customer can have multiple data planes and therefore multiple Kubernetes clusters. The way we set it up is basically every network block of GPUs a customer owns gets one Kubernetes cluster. And within that, we'll deploy a few services. We had a small controller service that basically ran, and that talked back to the control plane.
Thank you.
Hardware failure the only thing that can happen to an LLM? The only anomaly that you find?
Oh no, not at all, not even close. So the question was basically, are hardware failures the only anomalies? No, actually in every layer of the stack there are different anomalies. Sometimes, like it's always like a long list of random things. Like I can tell you recently we were training a model and we started hitting like throughput limits on S3, and then we had to switch from like S3 to a different place, right? Just like, or sometimes random Kubernetes things will happen, like the kubelet might fail, or like something goes bad in the operating system, and then you don't really detect it up front until you start noticing weird things in the networking or just like strange behaviors. There's also numerical problems that can happen, so sometimes the GPUs, they can be functioning okay, but then they'll start doing math incorrectly. And the only way you can really detect this is by running numerical tests on the GPUs. And the way you'll see this in your training run is the loss will just start to like spike, or like weird things will happen. So yeah, there's all sorts of things that can come up. It's not just like hardware breaking.
All right, just in the interest of time, I'm going to ask that we hold the additional questions for AJ to after the last talk. But thank you very much, AJ, for making this go. We have a great, obviously good interest coming from everybody here. Thank you very much. Transitioning now, we're going to move right into Ricardo's talk. And
all right, thank you. Thanks for having me here. Well, this is not as technical as the last talk, but hopefully this is entertaining and you learn something from whatever I'm going to be talking about today. So I'm going to be talking about LLM evals and cloud-native AI, and I just put the slides together maybe the last 2 or 3 days. So feel free to ask any questions if you have any. So a little bit about myself. I'm Ricardo Aravina, and I work for Tuera. I'm the head of Cloud Native there, and we make a product that allows machine learning engineers and data scientists monitor their machine learning models and diagnose their machine learning models. So a little bit, my slide is kind of weird here. Oh, okay. So just to get started, so all the, you heard about LLMs, right? So they hallucinate. So everybody understands that they hallucinate. So I asked a question to ChatGPT here about the meetup happening today, and you can see that basically it came out with a bunch of interesting stuff like cutting-edge technology, practical insights, network opportunities, but that's not actually the information of this meetup. Just make that stuff up. So consider LLMs hallucinatory all the time, right? So there's this solution called RAG, and they talked about the solution before, and which basically involves a prompt with a question, and then you create some embeddings with that prompt. You transform that into some vectors, and then you query that vector database with the embeddings and find adjacent embeddings and embeddings that are related, and then you grab those embeddings, and then you pick up chunks that are tied to those embeddings, and then you put that prompt together, and then you send that over to your LLM, and you get a more accurate response. So that's the whole idea behind RAG. But RAGs actually hallucinate too. They're not always, accurate. So in this example, we have Shayak. He's the CTO of our company, and you can see that the first part of this response is actually accurate. But when you look at the bottom part, you can see that it says that he's a member of England's AI Public-Private Forum and the OECD Global Partnership on AI, but that's not accurate, right? So this is where TrueLens comes in. So TrueLens is an open source project that allows you to track and evaluate LLMs. It does this by providing feedback functions to track different aspects of the life cycle of monitoring and tracking your LLMs. So in summary, it helps with the RAG triad. In this triad, you have a query, you get a context, you get a response, and then you keep querying the LLM to find more accurate responses. So it helps you with context relevance. That's a feedback function. It helps you with groundedness. It also helps you with answer relevance. Now, these are just sample feedback functions that are available in TrueLens, but we have several others. You can obviously go to the GitHub repository and find more information about them. So this is an example of context relevance. Sorry, go back. So, and finding that for this specific query, we didn't get enough context, and that's why we also got the wrong response here that I showed you previously about who is Kayak. So the feedback in TrueLens, you can see that given 4 queries to the LLM, it actually found 2 that are relevant and 2 that were not relevant at all. So you can see that it has a score of 0.55, and that means it's not, the context is not accurate. The perfect score will be a 1.0. That means that you will get the best context for your answer. So it also helps you with lack of groundedness. In this example, we have chat between a customer and a hotel manager, and then you get a response here, and you can see that with TrueLens, you break down the answer into 3 sentences, and these 3 sentences are scored, and the first one scores a 10, the second one scores a 1, and third scores a 10. So you have a total score of 0.7. That means you don't have full groundedness. And the reason is you have a score of 1 on the second sentence, that's actually they're not happy about the weight. And there's no evidence basically that this query or prompt makes it that the customers are not happy, right? So that's because there's no evidence, and that's why it scores low. And then finally, it helps you with answer relevance. And in this example, there's a 0.3 score with the answer. A sample question here is with which year Hawaii State song was written, and it actually replied with Hawaii Ponoai, which is the Hawaii State song. So that's the wrong answer. And if you can see the feedback here, you can see that only one of the answers here is relevant, and it gives you a 0.3 score of the query string relevance. And so TrueLens helps you with all these different things, like evaluating LLMs for honesty, whether they're harmful, whether the answers are being helpful, and within these, honesty, for example, it looks for context relevance, groundedness, whether to check an LLM is being harmless with their answers, it checks for toxicity, stereotyping, and whether the answers are also helpful in terms of conciseness and coherence. So TrueLens helps you with the life cycle of GenAI observability, with all that feedback between experimentation, validation, monitoring, and all of these different steps. And it also helps you integrate with like many of the different providers out there. You have to integrate with Llama Index and LangChain and the different models that are out there like OpenAI, Llama 2, Anthropic, and so forth. So enter cloud native AI. So this is something that I've been working on the last 4 or 5 months. So how to make it so that there's more cohesion between data scientists and DevOps engineers and developers. There's a gap there, so that's one of the motivations behind this. And then one of the things that we're looking at is the typical ML lifecycle or MLOps, where you have a data prep, and then you create a feature store, and then with that feature store, you create your model through training, and then you store your model artifacts in an artifact storage, and then you finally serve your model, and then you repeat the cycle over and over again. And why is it important? Because you look at things on scale. You've seen from the previous talks here. So you may handle lots of data. You want to automate your pipeline end to end. You want to monitor your end-to-end pipeline end to end. You also want to monitor the output of your LLMs. You want to serve large-scale APIs. So all the different aspects. And then you just want to look at these SRE type of aspects like reliability, performance, repeatable, user experience, whether your organization is growing and you're growing your data, you're growing your number of engineers or employees. One interesting one is multimodal models. So these actually require a lot more capacity. So for example, images and videos are more intensive in terms of compute. And finally, costs. You want to reduce your costs. And one of the relevant ones the last few years has been reducing your carbon emissions. So here's a simple demo of TrueLens with Docker and Kubernetes. And this shows the last end of the ML pipeline where you do observability on your LLM models. So briefly here, we have that YAML file that I showed you before, in which apply the TrueLens YAML file, created a TrueLens deployment, and a service got created. And you can see that deployment is up and running, and a service is created, and you have an IP address of 10.1.10.200.111, and then your pod is actually running. And now here we're getting that endpoint. This is running locally on Minikube. This is a pre-recorded video, so I ran this previously. And we get a URL, and then we just run a curl, and we see that it's actually responding. This is a TrueLens service with your LLM evaluations. So what it will look like, and on a leaderboard with all the different TrueLens evaluations, you will have your different evaluations for different models listed. So you can, in this example, you have 2 with the different feedback functions, context relevance, groundedness, and answer relevance. And if you dive deep into each one of these evaluations, you can look at each one of these feedback functions in detail and what they answered and exactly what feedback they provided during that evaluation. So in a cloud-native environment, why is this all important? Because in a cloud-native environment, you will have this high scale, and running on top of Kubernetes, a user coming in through an ingress controller, you will have something like TrueLens, scaling up and down using a horizontal plot autoscaler. And in the back, you will have your vector database, which we talked about before in some of the other sessions here. You will connect to a model, that could be a custom model, that could be something like OpenAI, that could be something like Anthropic. One of the things about having a custom model is that it could be more cost effective for evaluations, because like if you have a lot of calls to OpenAI, it can be very costly. And then at high scale, you would have something like that to store results in something like RDS or like MySQL or something that is open source database. And why is it important to have cloud native with AI is because you want to connect also to all these different providers, different LLMs, and there's frameworks like LangChain, and we talked about vector databases, Milvus, Chroma, Weaviate, and Pinecone are vendors, so either open source or vendors. And also you want to be able to access a lot of information through document stores, some of these tools like Reddit and Notion. So yeah, so one of the things that we're working on is this cloud native AI white paper, and we are publishing this in the next 2 or 3 days, probably on Monday, right before KubeCon EU. So check it out. This is a draft, but we'd love to have any feedback if you have any thoughts about it. So there's a lot of different things that we talk about, including the gaps between data science and DevOps and developers, to concerns with safety and LLMs and the data being used with LLMs, because that's data that is typically picked up from the whole wide internet. And we talked about the ML lifecycle or open source projects that are useful, like Qflow or MLflow. So a lot of information. So take a look and we love the feedback. And as far as TrueLens, we have a GitHub repository, so give it a start. So any start is actually welcome. So the more starts, the better. And enjoying the conversation. We have a CNCF tag runtime repo where we're doing a lot of the work, and then we also have a CNCF artificial group Slack channel where anybody can just join and have a conversation about cloud-native AI or all the challenges that you're having, and we can work on some of the things that we're thinking about in the future, like creating a cloud-native AI landscape, and we're also thinking about how to make it easier for people to get started with AI and cloud-native. For example, have a very basic Kubeflow environment where everybody can understand all the different aspects of machine learning, from having some data, prepping that data, training a model, and then serving that model. So having that life cycle in a small environment so anybody can learn that. That's all I have. So I'll take any questions.
Thanks, Ricardo. Nice talk. So there was a slide where you showed us different dimensions such as honesty and harmfulness. Does TrueLens provide numerical values for each of those dimensions, or is some combination of those?
You're talking about this one?
Not this one, there was another one. There was, for example, under harmfulness, you talked about, say, PII data and so on.
Oh, yeah.
Dimensions.
Yeah, this
Yeah,
one.
that one.
Yeah, so these are feedback functions that we provide with TrueLens, right?
So is there a numeric metric provided for each of these dimensions, or is there a combination?
So that's a good question. So the way we actually evaluate the LLMs is through using other LLMs. So we have a kind of like a base LLM, and it's, so we do have support for some other metrics that I'm not talking about here. There's Blur and other ones, but we think that those are don't work great for LLMs. So that's why we use the same LLM. So we baseline on an LLM, and then you can actually evaluate other LLMs based on that baseline, right? So it's all kind of empirical too. It's not because LLMs will never give you like right or wrong answers, right? So it's a lot of experimentation, like kind of trying it and going back and figuring out what works best. Yeah.
Thank you.
Mm-hmm.
Yeah, we got a great presentation. Thank you. One of my questions was, as I see the output, where in the flow of building an LLM app do you see this tool kind of fitting in? Is this during fine tuning? Is it when somebody's using it? Like once I have some output that I know it's a lie, like it's not a hallucination. What goes after that?
Yeah, so you can use the question is where in the flow you can use this the TrueLens tool, and then in the ML ops lifecycle, I would say. And the answer, you can use it in the beginning when data scientists are actually playing around with models, trying to get output, and maybe they create a small model and then get output. And maybe after training, they can also look at that. Or if you're training like a really large LLM after that training step. But you can also use it during production, right? So if you're serving, so you can continually get answers based on that and on your inference, right? So I would say the answer is like at different stages you can use this. It's not one specific stage.
During serving, who serves as the oracle?
Sorry, what's?
Like during serving, if I have to evaluate the response, who is the oracle?
Who's the oracle? Yeah, who's actually, so it's another, it will be another LLM, right? So if you go back to so for example, this diagram here, so you can see that sometimes it's good to have a custom model that gets you the baseline, because if you have something like OpenAI, you would just create a ton of APIs, and then that will be very, very costly, right? So and this becomes an issue with serving, right? With training, it's not that bad when you're creating and experimenting with the model, because maybe just like a few questions and answers or prompts and answers. But when in production you have hundreds and hundreds of users, then it will be very costly.
So just to follow up, like how do we solve the problem of hallucination if the custom model itself is an LLM?
That's where you, yeah, so goes back to the answer that for her question, basically. Yeah, so LLMs, they're always gonna hallucinate, so you have to experiment and have some sort of base LLM for answers, right? And then TrueLens has these feedback functions that I talked about that you don't you don't necessarily do just a single prompt and answer. It actually provides you more feedback by querying the LLM multiple times, because sometimes when you query an LLM multiple times, you get different answers, right? So and then we look at those, right? Like those different answers from LLM. Right?
Thank you.